Good morning, everyone. Today I'm going to record an audio lecture of mechanic and electricity on the topic of electrostatic field. Electric field, the space surrounding a charged body, is affected by its presence, and we speak of electric field existing in the space. Nowadays, Colombian forces acting between two charged bodies are explained in terms of the field concept as follows. If a charge plus Q1 is placed at any point, it sets up an electric field in space surrounding it. This field acts on the charge Q2 if placed in the field region. This action of the field of Q1 on Q2 results in the force F vector that is experienced by Q2. Thus, the field acts as an intermediary for transmission of forces between charges. We can also imagine that Q2 sets up field which acts on Q1 and produces a force minus F vector on it. This, however, should not be misunderstood that field is merely an aid in visualizing the mutual interactions of charges. The field is taken to be a self existence in reality and is a property assigned to every point in space in the vicinity of which one or more charged bodies are present. Electric field strength or field intensity. To define electric field at any point in space that is to be examined, we place a small test charge Q0, assumed to be positive for convenience, at that point. Let us further suppose that the total force experienced by this test charge due to other charges called source charge be F vector. The electric field strength denoted by E vector at that point is defined as the force per unit charge. Example on the test charge. E vector is equal to F vector upon Q naught. This is equation number 5.1. The electric field strength E vector is a vector quantity because F vector is a vector and Q naught is a scalar. Direction of E vector is the direction of F vector. That is, it is the direction in which a unit positive charge placed at the point of observation would tend to move, if free to do so. Further, it may be noted that the test charge Q0 used for measuring the field intensity should be vanishingly small because a large test charge might influence distribution of field due to the primary source charge, thus changing the very quantity we are trying to measure. Therefore, the above equation 5.1 should be replaced by E vector is equal to limit of Q0 tends to 0 F vector upon Q0. This is equation number 5.2. Thus, the electric field vector at a point is defined as the force per unit positive charge on a vanishingly small test charge at that point. The requirement that Q naught be vanishingly small, example Q naught tends to 0, leads to a fundamental and practical difficulty because the smaller possible magnitude of charge is that on electron or proton which is not near 0. We come across this anomalous situation mainly in microscopic cases where we deal with source charges equal to electronic charge. In macroscopic situation where Q is much greater than Q naught or Q is much greater than electron. I mean to say charge on electron or proton. The condition of defining E vector are generally satisfied. Unit of E vector. Equation 5.2 and 5.1 shows that electric field E is force per unit charge, so its unit is Newton per coulomb. Derivation of electric field from electrostatic potential. Electric field as gradient of electric potential. It is known to us that potential is a scalar function. Its value is different at different points. We have also seen that the potential function is defined as the line integral of electric field. If electric field is known to us, but we can also proceed in the other direction. Example from potential, we can derive electric field. We will see that the electric field will come out to be gradient of electric potential. Let us now calculate the electric field E vector. If potential function V is known throughout a certain region of space, let the value of potential at two neighboring points A and B, distance dl apart in the region be V and V plus dV respectively. Then the change in potential V, example dV, in going from A to B is given by dV is equal to curly V by curly x dot dx plus curly V by curly y into dy plus curly V by curly z into dz. This is equation number 5.3, where curly V by curly x and curly V by curly y and curly V by curly z represent rate of change of potential V along x, y and z axis respectively. Also from the definition of V, change in V, example dV is expressed as dV is equal to minus E vector dot dl vector. This is equation number 5.4. Comparing equations 5.3 and 5.4, we have minus E vector dot dl vector is equal to curly V by curly x dot dx plus curly V by curly y dot dy and plus curly V by curly z dot dz is equal to I cap curly V by curly x plus j cap curly V by curly y plus k cap curly V by curly z dot I cap dot dx plus j cap dot dy plus k cap dot dz. Here dl vector is a small displacement, so dl vector is equal to I cap dot dx plus j cap dot dy plus k cap dot dz. Therefore, minus E vector dot dl vector is equal to I cap dot curly V by curly x plus j cap dot curly V by curly y plus k cap curly V by curly z dot dl, or minus E vector is equal to I cap curly V by curly x plus j cap curly V by curly y plus k cap curly V by curly z is equal to I cap curly by curly x plus j cap curly by curly y plus k cap curly by curly z to the whole V equal to gradient of V. Therefore, electric field is equal to minus gradient of V. This is equation number 5.5. This is an important result which indicates that the electric field at any point is the negative of the gradient space rate of variation of potential at that point. The negative sign indicates that the electric field points from a region of positive potential to a region of negative potential, whereas gradient V points in direction of increasing potential V. If Ex, Ey and Ez are the components of E vector along x, y and z axis, then from equation 5.5 we get I cap dot Ex plus z cap dot ey plus k cap dot ez is equal to I cap curly v by curly x plus z cap curly v by curly y plus k cap curly v by curly z. Therefore, Ex is equal to minus curly v by curly x, Ey is equal to minus curly v by curly z, Ez is equal to minus curly v by curly dz. Thus, if potential function v xyz is known, the components of E found by taking negative partial derivatives of the potential function and from them E vector can be found. Equation 5.5 is very useful because it makes it easy to compute E at a point by first finding an expression for the potential at that point, and then using this equation we can compute E vector directly. This simplification is due to the fact that potential is scalar and involves algebraic summation rather than vector summation. Now we have a note here that the curl of the gradient of a scalar function is 0. Therefore, taking curl of both the sides of equation 5.5, we get gradient of E vector is equal to gradient into minus Poisson and Laplace's equation. The Gauss line differential form in free space is given by divergence of E vector is equal to rho by epsilon naught, where E vector is the electric field intensity and rho is the volume charge density in some region of space. Epsilon naught is the permittivity of free space. Also, electric intensity E vector is expressed as the negative of the gradient of potential V. Example, E vector is equal to minus gradient of V. Therefore, Gauss law reduces to divergence of gradient of V is equal to minus rho by epsilon naught, or divergence of gradient of V is equal to minus rho by epsilon naught. That is square of divergence into V is equal to minus rho by epsilon naught. This is equation 5.7. This equation is called Poisson's equation for the electric potential and gives a relation between charge density and the second derivative of potential in CGS ESU. This equation is written as divergence square naught V is equal to minus 4 pi rho. In Cartesian coordinates, it is written as curly square V by curly x plus curly square V by curly y plus curly square V by curly z is equal to minus rho by epsilon naught. The general form of Poisson's equation is divergence square dot phi is equal to f of x y z, where phi is a scalar function which represents gravitational potential in a region containing matter or the electrostatic potential in a region containing electric charge, a steady state temperature in a region having some source of heat, and f of x, y, z represents the source density. If the region of field is free from charge, example, if there is no volume distribution of charge in the given region, example rho is equal to 0, then the equation 5.7 reduces to divergence square V is equal to 0. This equation is called Laplace's equation. Obviously, this equation applies to the particular case where all the charges are distributed on surfaces of conducting bodies so that the volume charge density is 0 at all points. So, the electrostatic potential function in the space between the conductors and outside is defined by this equation. A function which satisfies Laplace's equation is called spherical harmonic function. The average value of function v of x, y, z satisfying Laplace's equation over any spherical surface is equal to its value at the center of the spherical surface. This important property of this equation has helped in solving many complex problems in physics. From mathematical viewpoint, the subject of electrostatic is merely the study of the solutions of this equation. Once V is found, the electric field can immediately be found by equation 5.5. So now we have some examples here. So the example number 1 is potential due to a point charge q at a distance r is given by V is equal to 1 by 4 pi epsilon naught dot q by r. Calculate E vector of r. The solution is from symmetry. E vector must be directed radially outward for a positive point charge. Consider a point P in the field at a distance r from the charge. It is clear that dV by dr at P has the greatest value. So, minus dV by dr will give the magnitude of E vector of r at the point P. Therefore, E is equal to minus dV by dr is equal to minus d by dr of 1 upon 4 pi epsilon naught into q by r, which is further equal to minus q upon 4 pi epsilon naught d by dr of 1 by r is equal to 1 upon 4 pi epsilon naught into q by r square. Example number 2. The potential function at a point is given by V is equal to x of 3y square minus x square plus z. Find the components of the electrostatic field at that point. The solution is electrostatic field E vector is equal to minus gradient of V is equal to minus square brackets I cap of curly V by curly x plus j cap curly V by curly y plus k cap curly V by curly z square brackets closed is equal to negative of square brackets I cap curly by curly x of minus x cube plus 3y square x plus xz plus j cap curly by curly y of minus x cube plus 3y square x plus xz plus k cap curly by curly z of minus x cube plus 3y square x plus curl xz square brackets closed is equal to minus I cap of minus 3x square plus 3y square plus z plus j cap 6 of 6xy plus k cap of x. Therefore, Ex is equal to 3x square minus 3y square minus z. Ey is equal to minus 6xy. Ez is equal to minus x. Example number 3. Show that the potential function V is equal to B of x square plus y square plus z square ka whole half does not satisfy the Laplace's equation. The solution is the Laplace's equation is the divergence of V is equal to 0 or curly square v by curly x square plus curly square v by curly y square plus curly square v by curly z square is equal to 0. LHS is equal to curly square by curly x square square brackets b of x square plus y square plus z square का whole half plus curly square by curly y square square brackets b of x square plus y square plus z square का whole half plus curly square by curly z square square brackets b of x square plus y square plus z square का whole half. Considering first term, curly by curly x square square bracket b of x square plus y square plus z square का whole half is equal to curly by curly x square brackets half of b of x square plus y square plus z square की power -1/2 into 2x is equal to curly by curly x of bx of x square plus y square plus z square की power -half is equal to bx of x square plus y square plus z square की power -3/2 into -1/2 into 2x plus b of x square plus y square plus z square की power -1/2 is equal to minus bx square upon x square plus y square plus z square का whole 3/2 की power 3/2 plus b by x square plus y square plus z square की power 1/2 which is further equal to minus bx square plus b of x square plus y square plus z square upon x square plus y square plus z square की power 3/2 is equal to b of y square plus z square upon x square plus y square plus z square की power 3/2. This is equation number 1. Similarly, curly square by curly y square is of b of x square plus y square plus z square की power half is equal to b of x square plus z square upon x square plus y square plus z square की power 3/2 is equation number 2. And curly square by curly z square of b of x square plus y square plus z square की power half is equal to b of x square plus z square upon x square plus y square plus z square की power 3/2. This is equation number 3. Adding 1, 2 and 3, we get divergence square of divergence of v is equal to 2b of x square plus y square plus z square upon x square plus y square plus z square की power 3/2 equal to 2b upon x square plus y square plus z square की power half which is not equal to 0. Divergence square of divergence into v is not equal to 0. So potential function v is equal to b of x square plus y square plus z square की power half. It does not satisfy Laplace's equation. So there are some more examples which are discussed later. So now we are going to discuss electric flux. Analogous to the flux discussed in Article 4.323b, we introduced the idea of electric flux. For this purpose, let us consider an electric field E vector in space, and in this space some arbitrary closed surface like a balloon of any shape S be immersed in the electric field. Such a surface and the field being suggested by field lines. Let us suppose that the whole surface is divided into a large number of small elements, which are so small that over any one element the surface is practically flat, and the vector field E vector does not change appreciably from one point of the element to another. The area of each element has a certain magnitude, and a unique direction, which is outward normal to its surface. Since surface is closed, so normal is from inside to outside. If the magnitude and direction of area of one such element be represented by vector ds vector, then the field lines are just the curves, the tangent at any point of which gives the direction of the electric field at that point. The density of these lines in a given region, which is defined as the number of lines per unit area passing through a surface normal to the lines, is the measure of the magnitude of electric field. The electric flux over ds is defined as d phi e is equal to E vector dot ds vector is equal to E vector dot n cap dot ds, where n cap is a unit vector normal to ds. It will vary from one element to another in accordance with orientation of ds on the surface. The above product is a scalar number. Let's now add up the flux through all the elements to get the total electric flux through the entire surface, which is a scalar quantity, and we shall denote it by phi e. Therefore, phi e is equal to summation of E vector dot n cap dot ds. This is equation number 5.11. Further, let the elements become smaller and smaller in size. Example, ds tends to 0. The sum given by equation 5.11 will tend to a surface integral taken over the entire closed surface. Thus, phi a is equal to limit of ds tends to 0 summation of all ds E vector dot n cap dot ds is equal to surface integral of our closed surface into E vector dot n cap dot ds is equal to surface integral over any closed surface is equal to E vector dot cos theta dot ds, where theta is the angle between vector E and vector n cap. The equation 5.12 gives the total electric flux through the entire surface S. It may be noted that flux through a particular element is positive, 0 or negative, depending upon the orientation of E vector and ds vector of the element. Thus, flux will be positive if the angle between E vector and ds vector is acute, and negative if the angle is obtuse. If the angle is pi by 2, the flux will be 0. For a closed surface, first, if E vector is directed outward at every point on the surface, angle theta between E vector and ds vector is acute at every way on the surface, and E vector dot ds vector is positive, and hence phi E over the entire surface is positive. Second is, if E vector is directed inward, then the angle theta between E vector and ds vector is obtuse everywhere on the surface. So, E vector to ds vector is negative. Hence, the flux phi E over the entire surface is negative. The unit of electric flux is measured in Newton meter square per coulomb. Gauss theorem or Gauss law in electrostatics. According to this law, the total electric flux of electric field E vector over closed surface is 1 by epsilon naught times the total charge Q enclosed inside the closed surface. If the charge is lying in the vacuum, where epsilon naught is the electric permittivity of the free space. Example, phi A is equal to integral over a closed surface of E vector dot n cap dot ds is equal to Q by epsilon naught. This is equation number 5.13. The charge inside the surface may be a point charge or a continuous charge distribution. Further, it may be noted that there is no contribution to the total electric flux if the charge is outside the closed surface S. The proof is, let us consider a single positive point charge plus Q placed at a point O inside any closed surface S of any shape. Let ds be a small area element ds of surface S at a distance r from Q. Let d omega by a small solid angle subtended by ds at O. Then d omega is equal to ds cos theta by r square, where theta is the angle between electric intensity vector E vector at ds and n cap, the unit normal vector over ds. The small electric flux through surface ds is d phi E is equal to E vector dot n cap dot ds, where E vector is equal to 1 upon 4 pi epsilon naught dot q by r square dot r cap. This is equation number 5.14, where r cap is a unit vector in the direction of vector r cap. Thus, electric field flux over the closed surface S is phi E is equal to integral over a closed surface E vector dot n cap dot ds is equal to integral over closed surface 1 upon 4 pi epsilon naught dot q by r square dot r cap dot n cap dot ds. This is from relation 5.14 is equal to integral over closed surface into 1 upon 4 pi epsilon naught dot q by r square dot cos theta dot ds, as r cap dot n cap is equal to 1 into 1 cos theta is equal to cos theta, which is equal to integral over a closed surface into 1 upon 4 pi epsilon naught q dot d omega is equal to q upon 4 pi epsilon naught integral over a closed surface dot d omega equal to q upon 4 pi epsilon naught dot 4 pi, where 4 pi is the total solid angle subtended by surface S at O. Hence, phi E is equal to q by epsilon naught. This is equation 5.15, which proves Gauss theorem. If instead of one point charge q, there are a number of charges q1, q2 up to qn enclosed by a surface S, then each charge will contribute to the flux. Let flux contribution by ith charge be phi of EI is equal to qi upon epsilon naught. Then the total flux phi E is equal to surface integral over closed surface E vector dot n cap dot ds is equal to summation of phi E is phi EI is equal to summation of qi upon epsilon naught is equal to 1 upon epsilon naught of q1, q2, q plus q1 plus q2 plus q3 up to n, which is equal to q upon epsilon naught, where q is the total charge inside the surface. So, phi A is equal to surface integral over a closed surface E vector dot n cap dot ds is equal to q upon 4 q upon epsilon naught, which is the equation 5.15a. Thus, equation 5.15a gives the total flux through a closed surface enclosing the net charge q. lying in vacuum. This equation implies that total number of lines of force originating from Q and cutting a spherical surface surrounding it is Q upon epsilon naught. It means that the total number of lines of force originating from a unit charge and cutting a sphere surrounding it is 1 upon epsilon naught. The closed surface taken in the electric field is called Gaussian surface. If the charge Q lies in a medium having dielectric constant K, then equation 5.15 is modified to phi of E is equal to integral over closed surface of E vector dot n capital ds is equal to Q upon K epsilon naught. This is equation number 5.16. If the algebraic sum of the charges within the surface is 0, example Q is 0, then phi E is also equal to 0. If there are some charges outside the surface, then these charges do not contribute to the value of phi E. This can be easily proved as under. Let us consider a point charge plus Q situated at O outside the closed surface. Let an elementary cone from O with small solid angle d omega cut the closed surface at two elements of area ds1, ds2 at the points A and B respectively. As at A, the electric field E vector is directed inward. So the flux from the intercept ds1 is equal to minus q d omega upon 4 pi epsilon naught. At B, the electric field E vector is directed outward. So the flux from the intercept ds2 is equal to q d omega upon 4 pi epsilon naught. Therefore, total flux through these intercepts is equal to minus q d omega upon 4 pi epsilon naught plus q d omega upon 4 pi epsilon naught is equal to 0. This also holds good for any other cone drawn from O intercepting the closed surface. Thus, the total flux over the whole closed surface is 0 when the charge lies inside. This is quite evident because when the charge lies outside, the total number of lines of force entering the surface is the same as that leaving it. Therefore, there is no net flux through the surface. A differential form of Gauss law. Now, when the charge has a continuous distribution over a volume V, if rho is the charge density, example charge per unit volume, then the total charge within the closed surface enclosing the volume will be given by Q is equal to volume integral of rho dot dV. Substituting this value of Q in relation 5.15a, that is surface integral over a closed surface of E vector dot n cap dot ds is equal to 1 upon epsilon naught into integral of V of rho dot dV. This is equation number 5.17. But from divergence theorem, surface integral over a closed surface of E vector dot n cap dot ds is equal to volume integral of divergence of E vector dot dV. This is equation number 5.18. Comparing the relations 5.17 and 5.18, we have volume integral of divergence of E vector dot dV is equal to 1 upon epsilon naught volume integral of rho dot dV. This is equation number 5.19. The equation 5.19 gives Gauss law in electrostatics. When there is enclosed a continuous charge distribution of charge by unit volume. Charge density rho. The above equation is true for any arbitrary volume. The integral on the two sides of equation 5.19 must be equal. Hence, divergence of E vector is equal to rho by epsilon naught. This is equation number 5.20. This is differential form of Gauss law. It is one of Maxwell's equation in electromagnetism. Gaussian surface. Gaussian surface is any closed surface of arbitrary shape drawn in the electric field to evaluate the total electric flux or surface integral of electric field E vector. While choosing such a surface, we avoid the charges on the surface itself. Importance of Gauss theorem. Gauss theorem is of great importance. Those situations in which evaluation of electric field by the application of Coulomb's law and superposition principle become very difficult, the results can be obtained by applying Gauss theorem with great ease by the purchase of the Gaussian surface which encloses the source charge. This is illustrated by following few examples. Electric field at a point charge due to an infinitely long line of charge. Let us consider an infinitely long straight uniformly charged wire so that it carries a positive charge of lambda per unit length. Let P be a point at a distance r perpendicular from the wire where we wish to find electric field strength due to wire from symmetry. E vector on either side of the wire must be perpendicular to the wire and directed outward. The magnitude of E vector will be same at all points equidistant from the wire. Let us consider a cylindrical Gaussian surface of length L around the line charge so that wire forms the axis of the cylinder and point P lies on the curved surface of the cylinder. Imagine a small surface area ds around P on curved surface. The electric flux through ds on the curved surface is equal to E vector dot n cap dot ds is equal to E dot ds. Since the direction of E vector and n cap, unit vector normal to ds is same at ds. The electric flux through an area ds on the plane surface of the cylinder is equal to 0 as the direction of electric intensity E dash vector and unit normal n cap to ds cap is 90 degree. So phi A is equal to E dot ds cos 90 degree is equal to 0. Thus, plane surfaces will not contribute towards the electric flux, and the contribution to the electric flux through the Gaussian surface will be due to curved surface only. Thus, total electric flux through the curved surface is phi E is equal to surface integral of E dot ds, where S is the area of the curved surface. Phi E is equal to E of surface integral of ds is equal to E into 2 pi RL. This is equation number 5.21, where 2 pi RL is the area of the curved surface of the cylinder. The charge enclosed inside the cylinder is equal to linear charge density into length, or Q is equal to lambda dot L. From Gauss law, phi E is equal to q upon epsilon naught is equal to lambda L upon epsilon naught. This is equation number 5.22. From relations 5.21 and 5.22, A into 2 pi r L is equal to lambda L upon epsilon naught. A is equal to lambda upon 2 pi epsilon naught. This is equation number 5.23. In vector notation, E vector is equal to lambda dot r cap upon 4 pi epsilon naught r. This is equation number 5.24, where r cap is the unit vector in the direction of r cap vector. Relation 5.24 gives the electric intensity at any point distant r from a long uniformly charged line of charge. Electric field at a point due to a uniformly charged spherical shell. Consider a thin spherical shell of radius r and center O. Let a charge plus q be uniformly distributed over the entire surface of the shell. The electric field due to charged spherical shell is radially outward, where q is greater than 0 and is spherically symmetric. Let us find where electric field at point P distant r from the center of the spherical shell. First, when point P lies outside the spherical shell. To calculate the electric field intensity at the point P distant r from q, imagine a sphere S with center O, radius small r, so that point P lies on the surface of the sphere, which forms a Gaussian surface. As all points of Gaussian surface are equidistant from the surface of the given shell from symmetry, we know that magnitude of electric field at all points on this surface must be same and directed radially outward as is positive, that is q is less than 0. Consider an area element ds around the given point P. The electric intensity E vector at P and unit vector n cap normal to ds both act in the same direction. D phi E is equal to E vector dot n cap is equal to E dot ds, and the total electric flux through the whole Gaussian surface is phi E is equal to integral over a closed surface of E vector dot n cap dot ds is equal to integral over a closed surface of E dot ds is equal to E of integral of closed surface of ds is equal to A into 4 pi small r square. Therefore, integral of closed surface of ds is equal to surface area of sphere of radius r. Since the charge contained by the Gaussian surface is q, according to the Gauss theorem, A into 4 pi r square is equal to q upon epsilon naught, where small r is greater than capital R, or E is equal to q upon 4 pi epsilon naught r square. This is equation number 5.25. In vector notation, E vector is equal to 1 upon 4 pi epsilon naught dot q pi r square dot r cap. This is equation number 5.26. Clearly, electric intensity at any point outside the charged spherical shell is such as if the entire charge on the shell were concentrated at its center. If phi if sigma is uniform surface charge on the spherical shell, then Q is equal to 4 pi capital R square sigma. Substituting for Q in equation 5.26, we have E vector is equal to 4 pi capital R square sigma upon 4 pi epsilon naught small r square dot small r cap is equal to sigma by epsilon naught dot capital R square upon small r square dot small r cap. This is equation number 5.27. Second, when the point P lies on the surface of spherical shell, example small r is equal to capital R, the Gaussian surface through point P will just enclose the charged spherical shell. Therefore, according to Gauss theorem, E into 4 pi capital R square is equal to Q upon epsilon naught, or E is equal to 1 upon 4 pi epsilon naught into Q by capital R square. This is equation number 5.28. Since Q is equal to 4 pi capital R square sigma, so E is equal to 1 upon 4 pi epsilon naught into 4 pi capital R square sigma upon small capital R square is equal to sigma by epsilon naught. This is equation number 5.29. In vector notation, E vector is equal to 1 upon 4 pi epsilon naught into Q upon capital R square dot R cap is equal to sigma upon epsilon naught dot small r cap. Third point, when point P lies inside the spherical shell. In such a case, the Gaussian surface is of a sphere of radius r small r less than capital R. As the charge inside the spherical shell is zero, so the Gaussian surface will not enclose any surface. Example Q equal to 0. Therefore, E into 4 pi r small r square is equal to 0 by epsilon naught, or E is equal to 0 for small r less than capital R. Example, electric field inside a spherical shell is always 0. The variation of electric field intensity E with distance r from the center of a uniformly charged spherical shell. Electric field due to a uniformly charged solid sphere. Consider an isolated solid sphere of charge Q having radius capital R and center O. Suppose we are to calculate electric field intensity E vector at any point P at a distance r from its center O. When point P lies outside the sphere of charge with O as center and r small r as radius, imagine a sphere S which acts as Gaussian surface. Let E be the electric field at point P due to the sphere of charge Q. It is evident that the field due to the sphere charge is spherically symmetric. At every point on the Gaussian surface, the field has same magnitude and is along normal to the surface. Therefore, the total electric flux through the Gaussian surface is given by phi of E is equal to integral surface integral of our closed surface of E vector dot ds vector is equal to surface integral over a closed surface of E dot ds is equal to A into 4 pi r square. According to Gauss theorem, A into 4 pi small r square is equal to q by epsilon naught. E is this is equation number 5.30. Therefore, E is equal to 1 upon 4 pi epsilon naught dot q by small r square, where small r is greater than capital R. This is equation number 5.31. It is the same as that a distance r from a point charge q. It means that for points outside the sphere of charge, the sphere behaves as if all the charge on the sphere were concentrated at its center. If ρ is the uniform volume charge density of the sphere of charge, then charge inside the sphere S is equal to volume of sphere of charge into volume charge density. Example, Q is equal to 4 by 3 pi capital R cube rho. This is equation number 5.32. Therefore, E is equal to 1 upon 4 pi epsilon naught into 4 pi capital R cube rho upon R square is equal to rho by epsilon naught into R cube, capital R cube upon 3 small r square. This is equation number 5.33. In vector notation, E vector is equal to 1 upon 4 pi epsilon naught into q upon small r square dot r cap is equal to rho by epsilon naught into capital R cube upon 3 small r square dot small r cap for small r greater than capital R. Second, when point P lies inside the sphere of charge. In such a case, Gaussian surface is spherical whose center O and radius OP dash is equal to small r. If Q dash is the charge enclosed by the Gaussian surface, then Q dash is equal to 4 by 3 pi small r cube rho. And the electric flux through the Gaussian surface according to Gauss law is phi E is equal to E into 4 pi small r square of small r less than capital R. E is equal to q dash upon epsilon naught 4 pi small r square. This is equation number 5.34. Or 4 by 3 pi small r cube rho upon epsilon naught 4 pi small r square is equal to r rho upon 3 epsilon naught. This is equation number 5.35. Also, q dash is equal to q upon 4 by 3 pi capital R cube into 4 by 3 pi small r cube equal to q into small r cube upon capital R cube. Therefore, substituting for q dash in equation 5.34, we have E is equal to q of small r cube upon capital R cube upon epsilon naught 4 pi small r square is equal to 1 upon 4 pi epsilon naught dot q r upon capital R cube. This is equation number 5.36. In vector notation, E vector is equal to small r vector dot rho upon 3 epsilon naught is equal to q r vector upon 4 pi capital R cube epsilon naught for small r less than capital